Okay, we're going to continue on here. We got into titrations last time, and we specifically talked about a specific type of titration, which is this one here, which is a titration of a strong acid with a strong base. So we looked at something like hydrochloric acid and some sodium hydroxide here, giving us some water and some sodium chloride here in this reaction. And we see our typical titration curve here, pH on the left there, and volume of sodium hydroxide being added. So again, in this case, we are adding the sodium hydroxide from the burette. I'll spit that out, I think. And we're adding it to our acid in our beaker or our flask. So that's, again, there really is sort of 4 distinct parts typically on any titration curve, including this one. The first one, as we talked about, is sort of right before you really add any base in this example here. So before we really start adding any sodium hydroxide, pretty much the only thing that we have in our beaker or flask to begin with is, in this example here, hydrochloric acid, which is a strong acid. Because we have not added any sodium hydroxide, the molarity of the hydrochloric acid will not change. So that really means to figure out the kind of our opening pH, we pretty much just need to go right into the pH equation here using the molarity of our strong acid, because that will give you pretty much your H+ concentration. When we actually start the titration, so from kind of like the first drop to our equivalence point, we are going to have a reaction that's going to occur, obviously the one I wrote up there on the screen, between the hydrochloric acid and the sodium hydroxide. As we talked about with buffers, and as we also talked about obviously with titrations here, remember that whenever you are constantly sort of adding volume, what is changing is the molarity will continuously change, because molarity, again, is moles per liter of solution. So the liters of solution will continuously change. The one thing that does sort of remain constant is the moles of, like, your HCl. You only have so many moles of it in there to begin with. So we do need to do an ice table here, because we are going to get a reaction between the hydrochloric acid and the sodium hydroxide. And as we talked about before, and as we sort of did with buffers, we do need to do that ice table in moles to begin with. And really at the end of that first ice table, and in most situations, if you do an ice table in moles, at the end, you should then convert everybody back to molarity at the end of the table. And in the case of a titration, we would use the total volume at that point to do that, which would be obviously the amount of acid we started with in our beaker and how much, obviously, sodium hydroxide in this example that we added to it, converted to liters, would allow us to convert back to molarity. Because you're before the equivalence point and pretty much at the equivalence point, as we talked about, the moles of the acid will equal the moles of the base when you do reach the equivalence point. We actually have less base than acid in this case. So as we talked about, really the base is sort of like the limiting reagent in this case, and the acid is like the excess reagent. So really what's going to happen as a result of that ice table is you're going to have plenty of acid there to take care of all your base, your sodium hydroxide that you're adding. So the purpose really of the ice table is to figure out what the concentration of your strong acid is after it reacts. So to get kind of your new concentration of the strong acid after it reacts, in this example here with sodium hydroxide. At that point, what you really will be left with is 2 things. You'll be left with a salt, that sodium chloride, for example, that is a neutral salt, so not going to really screw up the pH. And you'll be left with, obviously, the hydrochloric acid that's left over at the end of the ice table. Again, that was still a strong acid at that point, which means you could go into your pH equation, obviously, and get the pH at any point from when you add the first drop to get to the equivalence point. So it requires at least 1 ice table there in that sort of region, this sort of second region here. It needs an ice table, and really, again, the purpose of that ice table is to figure out what that new concentration of your acid really is so that you can calculate the pH. That then takes us to, as we talked about, sort of the third important part on this titration curve. We do typically see, as we also talked about last time, that we do typically see a jump in pH to the equivalence point, and then we typically will see a jump in pH sort of after the equivalence point. And as you also approach that equivalence point in pretty much most titrations, it doesn't take a lot of volume to change the pH a lot. So I think we might have talked about it as well. You know, if you've done titrations before, which you should have in 200A, you know, this is really the reason why when you add like a drop or two and it's like not really pink, and then it goes like super pink from just like a drop or two, is because as you approach the equivalence point, it doesn't take a lot of volume to change the pH a lot. And how indicators like phenolphthalein work is on a pH range. So just by adding a drop or two is enough sometimes to make the pH actually go a lot higher. And thus, when you see visually, is it just went like super pink, you know. And the reality, as we talked about last time, is, you know, if you really were careful in your titrations and it went super pink and you really only missed it by a drop or two, volume-wise, it's really not that big of a deal, because if you're up here, that's really the same volume as where the equivalence point is and so forth. Now, if you're really careless and just let it open and shut it at some point, you could really find yourself with a dark pink that puts you way over here, which obviously is way too far, obviously, from the equivalence point. So as we talked about, you know, sometimes it's more important that your volumes sort of agree, you know, when to reach the equivalence point, and that's usually a good thing. But what we are at the equivalence point, we do have equal moles of acid and base at that point. And you really don't need a nice table in this particular type of titration, because it's basically going to zero out your HCl. It will zero out your sodium hydroxide. And really all you'll be left with when you do reach the equivalence point is that salt, which is sodium chloride in this particular case. And as we just mentioned a second ago, that obviously is still a neutral salt. So really the pH here should be 7 in this type of titration. So when we do it today, when you get close to the equivalence point, it should be around 7 is really where that, you know, equivalence point should be. And then obviously the fourth sort of part of the titration curve, which kind of brings us up and around here in the bend, is really once we kind of go past that equivalence point. And really when we go past the equivalence point in this particular type of titration, since at the equivalence point, the moles of each of those guys are pretty much equal, what ends up happening is as you go past the equivalence point, the sodium hydroxide in this example, or whatever base you're adding, you now have added way too much, basically. And we get sort of a flip that occurs where the acid in this case, the HCl, becomes like the limiting reagent, and like the sodium hydroxide now, because that pink color didn't stop you from stopping your titration, you just kept adding sodium hydroxide, now becomes like the excess reagent. So what ends up happening past the equivalence point is we really don't have enough acid to take care of all that sodium hydroxide that we're adding. And the result of that is we will end up with excess amount of sodium hydroxide, because pretty much at that point, you're just dumping in hydroxide into the solution, which is also why we see a pretty big jump after the equivalence point, because you're just dumping in basically hydroxide. So after the equivalence point in this type of titration, we still need to do an ice table. It obviously still needs to be done in moles. The purpose really of this ice table is actually to figure out what is the concentration of your strong base that you will have left over at this point, because it's the excess reagent. Again, you want to convert those moles back to molarity at the end of that ice table. And that will allow you to get, again, not the pH in that case, right? Because that is basically OH minus. That will allow you to calculate the POH. And then from that, you could take 14 minus it and then get yourself to the pH. So in this type of titration, those are really the 4 critical points along the way. Pretty much you got to do an ice table at steps really 2 and 4 here in this type of titration. You could go right into the pH equation at the very beginning before you add anything, and then really at the equivalence point here, you don't really have to do much other than know this should be 7, because there's all that's left is a neutral salt. Any questions on any part of these titration here? So why don't we try one? Why don't we just do, let's do one here. Paper. What is the pH after 27 milliliters of 0.1 molar sodium hydroxide is added to 25 milliliters of HCl. All right, take a minute, see what you have. So again, same setup here. We're adding the sodium hydroxide to the HCl in this titration. And the molarity of the HCl is also 0.1 molar. That would probably be helpful. There you go. All right, so what is the pH in this titration here? Again, adding the sodium hydroxide to our 0.1 molar HCl that we started with 25 milliliters. I'll do it as well. We'll see if we end up the same spot. Let's take a look here. So clearly we're adding some sodium hydroxide to our HCl. So again, our sodium hydroxide up in the burette, HCl down in the beaker, and obviously we are adding it to it. So we are going to obviously get a reaction between the two. It's going to be the same reaction. We're going to need to do an ice table here, right, to sort of figure out things. Should I do that table in moles or molarity here? We should definitely do it in moles. So that's probably maybe where we want to start. So if we want our moles of sodium hydroxide, that would be converting my milliliters into liters, 0.027 liters, timesing it by my molarity, which is 0.1 moles per liter. Liters will cancel out in that case there, 0.1 times 0.027. 0.0027 moles of our sodium hydroxide. We will do a similar calculation for our HCl here. That would be 0.025 liters, which is our 25 milliliters converted to liters, 0.1 moles per liter, and that will get us 0.0025 moles of our HCl. Any questions on that part there? Now we can go into our ice table. So we're going to get our HCl that's going to react with our sodium hydroxide here. Obviously going to give us the same reaction we saw earlier, our water plus our sodium chloride here. So initially here, we do have 0.0025 of this guy. And that is moles. We got 0.0027 of this guy and nothing of this guy. Now, at this point, you know, it's always a good idea to kind of know where you are in the titration. So this is what we're starting with. This is what we are adding. So if you weren't sure where you're at in the titration, just by looking at those numbers, it should tell you. And where are we? Are we before, at, or after the equivalence point? We are definitely after the equivalence point. I know that because if we were at the equivalence point, the moles of the HCl and the moles of the sodium hydroxide should be the same. And in this case, we actually have more moles of the sodium hydroxide, which would imply we have blown past that part, right? And we're continuing to add more sodium hydroxide. So again, don't overlook your ice table, as it could kind of help you sort of figure out where you're at. We should know at this point, pretty much we are now just dumping in some base, right? Which means when we're all said and done, our pH probably should be acidic, neutral, or basic. Should be basic. So these are things you want to think about as you're going through these calculations to make sure when you're done, you know, everything does make sense. So as we talked about a second ago, pretty much because we are past the equivalence point, we have pretty much excess amount of sodium hydroxide. Our HCl becomes the limiting reagent. So the change part here is actually going to be the moles of the HCl. Easy way to remember that is, as much as you're going to want to do it, you cannot have a negative number. Yes, and I say that because people do negatives all the time on these because they feel like that's the right move. But you can't have a negative number, so it's always got to be the smallest number there. So that's a good thing to keep in the back of your head if you're in that position on a test where you decide you want to do the opposite and end up with a negative number. That's going to zero out our HCl at this point. That is 0.0027 minus 0.0025. That is a lot of zeros, but it's 0.0002 moles of this guy and 0.0025 moles of this guy. At this point, again, really good practice to convert back into molarity here. Our total volume at this point is, we added 27 of that guy. We started with 25 of that guy. That's like a 52 milliliters, right, is our total volume at this point in the titration, which means really we want to come back here and divide these guys by 0.052 liters. That is going to get me, call it 0.00385 molar, and 0.025 divided by 0.052. That is, lost a zero there, 0.0025 divided by 0.052. 0.0481 molar. So now what we want to do, again, if you're not sure what's going on at this point, hopefully you sort of have an idea of what should be happening from our earlier conversation. But you could also still look at your ice table, and we have this guy left over, and we have that guy left over. First off, is that a buffer? Again, that is not a buffer. And that is also a very common mistake people do. It's like, I got two numbers, I'm going to throw it into the Henderson-Hasselbalch equation. Those are not buffers. So we want to analyze what we got going. As we talked about before, this is a neutral salt, right? Which means we're not going to worry about it, which means we're really not going to worry about this guy. That really means what we have left over is sodium hydroxide, which is a strong base like we anticipated it should have been. And that means that really the OH minus concentration in this case is 0.00385. That is going to allow us to calculate the POH. POH here is going to be minus the log of 0.0038. I lost a 5 there. I know. I'll put a 5 back in. Put a 5. Minus the log 0.00. 385. There we go. That gives us a POH of 2.41. Again, also a very common mistake. If you thought that was the pH from our earlier conversation, that should be clearly wrong. Yes. So our pH here would then be obviously 14 minus our 2.41. And with the little room I got left there, like an 1156 pH. Which is definitely a basic pH and what we would expect to be happening at this point in the titration, because we're basically just dumping in some hydroxide. What's that? What you got? What? You are correct. I just can't see it. It does say that on my calculator. 11.585. Thank you very much. So 11. I'm not having a banner week with looking at numbers here today. So I'll just write it right here. 11.59 if you actually read the calculator correctly, which would be good as well. Thank you. Other questions on that? And we can just check real quick, since this is actually the titration from this titration curve. We were at 27, which is kind of between these two numbers, and that's where we're at, 11.59, which is obviously less than 11.75 and a little bit more than the previous one. So we did pretty good on that. All right, question on strong acid, strong base titration. So, okay. We're now going to talk about the next type of titration, which is a weak acid, strong base titration. So something like sodium hydroxide, something like acetic acid, which is a weak acid, and sodium hydroxide, which is a strong base. So much like the previous one, we have our sodium hydroxide up in the burette, and we are adding it to our acetic acid here. So we do see a similar type of titration curve as we saw with the strong acid, strong base titration. We see the typical S curve. We got really the same 4 points on this curve as what we had on the previous one. We have that first point there, which is, again, before we add any sodium hydroxide. We have kind of the second part of the curve, which is once we start adding before we reach the equivalence point. The third part, again, the equivalence point. And then again, the fourth part here is going to be after we go past the equivalence point. So we have similar type of calculations that are going to occur and really the same sort of 4 points. But this type of titration is a little bit different in terms of how we get to our pHs. So let us go through each of these parts here and kind of see how we get there. So we're going to start at the very first point, which is before any sodium hydroxide, or base in this case, is added. So a reminder that what we got going on here, again, our sodium hydroxide up in the burette, our weak acid here in the beaker. So before we start this titration, the only thing that we really have in the beaker is the weak acid, like our acetic acid. Now, if it's a weak acid like acetic acid, and I haven't added any sodium hydroxide, I don't have to worry about moles, right? I can use molarity. How do I calculate the pH of a weak acid? So to calculate the pH of a weak acid is like what we talked about previously. It is just a Ka problem, right? You need to do an ice table with the weak acid. So we'll use acetic acid here. That's going to dissociate into H plus and acetate. And as I mentioned before, since we have not added any sodium hydroxide here, we could just use our initial molarity there, right, as our number. The rest of the table here will be like a regular Ka table. These are going to be zeros. Since we're using molarity here, we'll use some x's, plus x and plus x. This is going to be your molarity initial minus x, x, and x. This would go into our Ka expression, which would be H plus and acetate divided by acetic acid. This would equal our Ka value, which would be 1.8 times 10 to the minus 5 in this particular case. Like normal, right, we would throw our x's into this. We would solve for x. And again, you can probably make an assumption here or solve it some other way. Once we solve for x, we could go back to our ice table and we can clearly see that x is equal to the H plus concentration, which means that would give us the H plus concentration, and that would then allow us to go into our pH equation at this point. So you could clearly see here, unlike the previous titration curve, a little bit more involved here to get to the pH, since we are dealing with a weak acid versus a strong acid. In the previous titration, we could go right into the pH because it was a strong acid. It's going to dissociate. Here we got to do really a Ka problem, ice table with molarity and x's, and then obviously using our Ka value, calculate the pH. Any questions on before the titration begins? Okay, so once we decide I am ready to add from our very first drop of sodium hydroxide to before the equivalence point, in this second region of the curve, we are obviously going to be adding volume here, which means we are going to get a reaction that's going to occur. So before the equivalence point, and we're going to be obviously adding sodium hydroxide at this point. So we will definitely get a reaction in this case between the weak acid and the sodium hydroxide. And that would get us our acetic acid and our sodium hydroxide doing a little double displacement action, going to get us a sodium acetate that's going to be formed. and a little bit of H2O there. We are going to need to do an ice table here. Should this ice table be molarity or moles? This one should be moles. Again, we're adding volume here, so we want to do this in moles. So just like on the previous titration, I'm just going to make up a number for our acetic acid. I'm going to go with the 4 like we did last time. So we're going to say that we are starting with 4 moles here. We are obviously adding our sodium hydroxide in this case. So since we are before the equivalence point, should the moles of sodium hydroxide be less, equal to, or more than the acetic acid? Should be less, right? Because again, at the equivalence point, they're equal. So we haven't reached there. We're working our way up there with the sodium hydroxide. So it should be less, and we'll go with 2 moles here. Again, just making up the number. We have nothing here. So much like what we talked about previously here, at this point, it is the sodium hydroxide that is really the limiting reagent. We got enough of the acetic acid there to take care of it. So again, the smaller number should be our change. So the change here should be minus 2 moles, and plus a 2 mole over here. That means at equilibrium, we got a couple moles of this guy. We got none of that guy. And we got a couple moles of this guy. Any questions on the ice table here? At this point, we can take our total volume and convert these guys back into molarity, which is a really good idea. Trust me when I say that. By obviously using the total volume, we can convert each of these guys back into molarity. At this point, if you're not sure how to get the pH, look at your ice table and see what you got left over. At this point, we have some acetic acid and we have some sodium acetate. Are those two things related to each other? They are related to each other. The acetic acid is a weak acid. The sodium acetate is its conjugate base. And when you have a weak acid and a conjugate base, you have a buffer. Yeah. So those guys are related to each other. And basically what we just formed is a buffer at this point. And that means that we know how to get the pH of a buffer, right? We could use the Henderson-Hasselbalch equation here to do that. That's probably the easy way. So you could use the pH is equal to the pKa plus the log of the base over the acid. If you wanted to, you could also still do an ice table instead of the Henderson-Hasselbalch equation. So I'll go with an R. And if you're going to do that ice table, again, it really is the acetic acid you probably want to work with here since you have the Ka value for it most likely. And the most important thing, if you choose to do an ice table instead of the Henderson-Hasselbalch, is you should have obviously the molarity from above there. This should be 0. And most important, you actually have this guy that should go there. And it's a very common mistake. People will put 0 right about there. And again, at that point, you are not doing a buffer. You are doing a weak acid problem, and you will get the wrong answer. So the rest of the table obviously are X's. And then obviously you would solve for X. And X would again equal your H plus concentration, which you could go into the pH. Again, if I was choosing, I probably would go with this one, a little less room for error. But if you're comfortable doing the ice table or would rather do the ice table, you absolutely can do that as well. So you can see here on the second part of this type of titration, very different than what we had going on with the previous type of titration. You will always, at this point in region number 2, end up with a buffer, and you always could use the Henderson-Hasselbalch. And that's why we don't see such a dramatic rise in the pH. It's kind of buffering through here, yes? And so at the second part of this titration curve, you need to do a minimum of 1 ice table to get really your concentrations of your buffer, and then into the Henderson-Hasselbalch equation are 2 ice tables. First one to get the concentrations of your buffer. Second one, really a ice table buffer problem is what you would need to do. Any questions on that there? By the way, that's also why if we back up to step number 1, we see that our starting pH is a little bit higher in terms of the acid than our strong acid, because it's a weak acid, not going to give away as much H+. So you start a little bit higher on the pH scale there as well. So as we move through 2 here, we're buffering, and kind of like what we talked about buffers, at some point you're going to blow through the buffer, and that is where we see a big jump in pH to get us to the equivalence point. So we kind of are creating a buffer, got kind of a buffer situation happening, but we're continuously adding our sodium hydroxide, kind of like what we talked about with the buffer, right? As you add one, right, one part of the buffer gets used up, and that's basically what we're doing here in the titration, is we're continuously chewing up, in this case, the acid part of the buffer, which means at some point we're going to blow through the buffer part of it, and that's why we kind of see that jump in pH to the equivalence point. Any questions on that? All right, then that will take us to the equivalence point, and let's see what we got going on at the equivalence point. So at the equivalence point here in this titration, again, there's a couple of ways, by the way, I think we might have talked about, but just in case, they may not always tell you the volume to reach the equivalence point in a problem. They'll just simply ask, what is the pH at the equivalence point? So there's several different ways you could figure out, what is the volume to get to the equivalence point, as it is important to finish out the calculation to figure out the total volume, right, that you added at that point. If it is a one-to-one relationship between the acid and the base, you could do M1V1 equals M2V2, and you will get the volume that you need to reach the equivalence point. M1V1 could be your acid stuff, and M2 and V2 could be your base type information. That's really stoichiometry as you're doing that. If it's not a one-to-one, you should do some stoichiometry, some real stoichiometry. The other way is, as we'll see here in just a second, you will know the moles that you should have of your base, and you will know the molarity of it. So you can use the molarity and the moles to figure out the volume you would need to add to get there. So at the equivalence point, we are still going to have our same reaction, which is our acetic acid reacting with our sodium hydroxide here, still forming our sodium acetate and our water. And again, we want to do this in moles, as we've been talking about. So I'm just going to make up my number here again as 4, just to keep the numbers pretty easy to look at. And obviously, we are adding sodium hydroxide. So at this point, if you weren't sure about the volume to get there, the one thing you should know is the moles of sodium hydroxide at this point should be less than, equal to, or more than my acetic acid. Should be equal, right? That's basically your definition of equivalence point. So again, even if you didn't have the volume given to you, you could get to the ice table and go, all right, I know I got 4 moles of that. I should have 4 moles of the sodium hydroxide. And this is what I was saying a second ago. You most likely will have the molarity of your sodium hydroxide, which means you would have the molarity, you would know the moles. You could use just rearranging the molarity equation to figure out how much volume of sodium hydroxide you would need to produce that many moles, and that would allow you to figure out how much you need to get to the equivalence point. So there's a lot of different ways, if they don't give you the volume to reach the equivalence point, that if you look at your ice table, look at the information given to you, you can kind of work backwards and sort of figure those things out. At this point, obviously, we're going to have 0 this guy. The good news is here at the equivalence point, you can't go wrong. There's only one number to choose, so choose that number. So this is going to be -4, and a +4 moles. That means, as we expect here at the equivalence point, goodbye acetic acid, goodbye sodium hydroxide. We are left here with our moles of sodium acetate, which again, using the total volume, we can then convert it back to molarity at this point. First off, any questions on that ice table or what is happening here at the equivalence point? So we do want to look at our ice table again to help us figure out what is going on. And obviously at this point, that is all we got going on there is sodium acetate. So what is sodium acetate? That is a salt, yes. So when we have a salt, there's one question we want to ask ourselves, which is, will that salt go through hydrolysis, right? Will this salt go through hydrolysis? Well, let's take a look at the salt and see. So this is sodium acetate, which when it goes for a swim, will produce sodium ions and acetate ions, right? Let's start with sodium. In terms of a salt, are we concerned about sodium? We are not, because it is group 1. It basically comes from like really sodium hydroxide. It is a strong base really, which means it is a neutral salt, right? pH is 7. What about acetate? Where does it come from? Yeah, it comes from this guy right here, right? That is acetic acid. Acetic acid is a strong or weak acid. It is a weak acid, hence the name of this titration, right? Weak acid, strong base. Which means if acetic acid is weak, its partner, which is acetate in this case, is it weak or strong? It is strong, I think I heard. Yes, it is the opposite relationship. So will acetate go through hydrolysis? It will. So at this point in the titration, you are left with a salt that came from a weak acid, which means it's going to go through hydrolysis, which means the lovely part of this calculation is our first ice table is then followed by a second ice table here, where we're basically going to now do a hydrolysis problem. And that means that we would take the part of the salt that will go through hydrolysis, and it will react with water. Now, again, if you're not sure how it's going to react, we should think about it where it came from. So again, it came from acetic acid, which is an acid, which means really the acetate here will be its conjugate base, which means when it reacts with water, it will react like a base, which means should it donate or accept an H+? It should accept an H+, right? Because it's going to act as a base. The result of that is, as we talked about with salts, it will always make where it came from, which is acetic acid. And we will then produce some hydroxide as the water gives up that H+. Just like when we talked about with salts, without even finishing the calculation, my pH should be acidic, basic, or neutral. It is going to be basic here as we just produce hydroxide. So again, a good thing to think about, a good thing to know, because when you get your answer at the end, you should hopefully have a basic pH here. Also, when I calculate this, Ka, Kb, Kw, yeah, we should be using a Kb. So just like we talked about with salts, you want to think about these things because, and again, in this problem, you probably have just the Ka given to you, so you got to do that conversion. This is also why it is a really great idea, and you should always do it, to convert this guy into molarity, because when you do this second table, you need molarity, not moles. So just convert it into molarity up front, and you'll be in good shape. That is actually where our initial concentration will come from. It is the molarity from above. Yeah, it is this guy. That is basically our source of acetate. This is going to be a 0, a 0. Change is going to be minus x, and plus x. That means at equilibrium here, our molarity minus x, and x. Here, as you just mentioned, we want to go into the Kb. So again, our Kb would be Kw divided by Ka, right, to get us to Kb. Kw being obviously our 1 times 10 to the minus 14 number. We would use the Kb. We would solve for x. X in this case, we also need to keep in our head, is equal to what concentration? It is the OH minus concentration, not the H plus concentration. So that is going to equal the OH minus concentration, which will allow you to get to the POH, and you do a little 14 subtraction there, will get you to the pH. So you can see here in this type of titration, much different than just laying up a 7 at the equivalence point here. And this will always happen in this type of titration. Once you reach the equivalence point, because you're starting with a weak acid, you will always be left with a salt that came from a weak acid, which means it will always go through hydrolysis, producing hydroxide 100% of the time, meaning that the pH at the equivalence point should be basic. Also, again, you need to do it basically 2 ice tables at this point. Any question on any part of that there? That again is why when we look at our titration curve here and we come to the table, we see that our pH there is definitely basic. It's also why when you did your titrations in 200A, and most ones that you did, you use phenolphthalein because it works from a pH of 8.3 to 10, which is right there at the equivalence point. When it should turn color, that's why we chose that phenolphthalein usually for that type of titration. Any questions on the equivalence point part? Okay, so again, at the equivalence point, you do need to do really 2 tables. First table is really just to figure out what is the concentration of your salt. The second table is a hydrolysis salt problem to get to the pH. Now, step number 4 here, again, the equivalence point doesn't stop you. You're going to continue on adding sodium hydroxide here. So let's talk about what happens at that point in the titration, step part number 4, which is after the equivalence point. So clearly we are still having the same reaction occur. That is our acetic acid plus our sodium hydroxide here, which gives us our sodium acetate and our water. Now, again, at this point, we're just going to do this in moles like everything else because we're still adding volume. I'm going to make up my same 4 moles that we've been using the whole time through here. Because we are after the equivalence point, the moles of sodium hydroxide should be less than, equal to, or greater than 4. Should be greater. Again, we're just dumping sodium hydroxide in at this point, so we should have more moles of it. We'll go with lucky number 6 there, see how that works out for us. We get the same thing that we talked about previously here. We're going to get a switch is going to occur. At this point, our acid is actually going to be used up because it's the smaller number, it's the limiting reagent. So the change here is again -4, not -6. You're going to want to do it. Don't do it. That is going to zero us out of acetic acid, which is what we would expect to happen since we're going way past the equivalence point, perhaps. We got 2 moles of this guy, got 4 moles of that guy. Just like everything else, we're going to be good chemistry students and convert it back to molarity at this point. Now, when we look at this, we got a couple of things left over here in our ice table. We got some sodium acetate, and we have some sodium hydroxide. Are these 2 things related to each other? They are not. This is not a buffer, but a very common place where, again, people want to put it into the buffer equation because they got the 2 numbers. So we really got 2 things happening here. We got 2 things that could affect the pH. As we saw in the previous step at the equivalence point, right, this salt will go through hydrolysis and really act as a base, right, and produce hydroxide. And we have sodium hydroxide, which is what type of base? It's a strong base. Now, between the 2 of them at this point, which one would be the major contributor of hydroxide? It would be the strong base at this point, the sodium hydroxide. The sodium hydroxide just needs to go for a swim, and it's going to break apart and produce hydroxide, right? The acetate's got to go find some water, do a little reaction, you know, produce some hydroxide. So out of the 2 of them at this point in the titration, the major contributor is going to be the strong base. which means we typically ignore the contribution from the salt to keep things a little bit simpler. And we really do look at just a strong base at this point. That makes the calculation a lot easier because what we have now is just the concentration of our strong base, which would be the concentration of hydroxide, which should allow you to get to the POH at this point and then to the pH. So typically after the equivalence point in a titration where you're dropping base, you're basically dropping a very strong base, which means it's really going to be the one contributing the majority of the hydroxide to the solution, and it really will be the one that will determine the pH of it. So we ignore the salt's contribution at that point, and we look at just the strong base. We don't do that at the equivalence point because there is no sodium hydroxide left at the equivalence point, right? Which means the only thing technically kind of producing hydroxide is actually the salt, which means it is sort of important at that point. But at this point, in comparison, sodium hydroxide much stronger base than the acetate. Any questions on that? Yeah. That is, so in this type of titration, before the equivalence point, you will always end up with really an acidic buffer at that point. So at the fourth part here, you do need to do a ice table. The purpose really of the ice table is to get the concentration of your strong base you got left over, and then you could go into the pH and the POH and then to the pH equation. Any questions on any parts of that titration curve? So why is it important to know where you're at? Because really, although it seems very crazy, this titration curves and all the calculations we just talked about, they really are all the calculations we've done previous to this. Yeah. So the key is to know where you are, because if you actually know where you are in the titration curve, you should know what type of problem you should be doing. If you know you're at the very beginning of this type of titration, you should be doing a Ka problem. If you're like at the start of the titration before the equivalence point, that is going to end up as a buffer. If you're at the equivalence point, that is going to be a hydrolysis problem. And if you're past the equivalence point, it's really just going to be a POH problem. So knowing exactly where you are in the titration curve, and many people just browse right over that, not really concerned about it, they just jump into the calculation. You should actually know before you pick up your pen to do the calculation what type of problem you should be doing. And if you kind of know where you're going, right, with directions, it makes it a lot easier to get there, yes. Even though sometimes we don't like to ask for directions. We know where we're going as we circle the same street 4 times. But, you know, if you kind of know where you're doing before you start it, you should be able to you really do the calculation a lot easier. Where people really do run into problems, they just jump in and try to figure out, okay, kind of what's going on as you're going through it. Having some thought about it before you start it, very, very helpful. Any questions on this here? Okay, we're going to then talk about, actually, let's try one here. Let's do, before we go on, let's go with, what is the pH after, let's see here. Let's do 21.5 milliliters of 0.1 molar sodium hydroxide is added to 25 milliliters of 0.1 molar acetic acid. The Ka value for acetic acid, 1.8 times 10 to the minus 5. Okay, let's take a look here and see how we're doing. So obviously we have the same titration. We obviously have added some sodium hydroxide here. So we should obviously know we need to do an ice table for sure. Can't really go wrong with that usually in this class. We also should know that we should do it in moles because we're adding volume here. So let's start with that. Let's get our moles of each of these guys. So our moles of sodium hydroxide converting our volume into liters, 0.0215 liters, times in it by our 0.1 moles per liter, and 0.0215 times 0.1. Going to give us 0.00215 moles of sodium hydroxide. We'll also get our moles here of our acetic acid the same way. So we have our 0.0250 liters and our 0.1 moles per liter here. Again, our liters will cancel out, getting us 0.0025 moles of our acetic acid. Any questions so far? Then we can go into our ice table here. So we'll do our acetic acid plus our sodium hydroxide, giving us some sodium acetate and some water. Initially, we'll use our moles we just calculated, which is 0.0025 moles. This is 0.00215 moles, and this is 0. So the first question is, am I before, at, or after the equivalence point? We are before the equivalence point. Again, we know that by looking at our sodium hydroxide moles, which is what we're adding. It is less than the moles of the acid we're starting with. Based on our conversation, we should know we should end up with an acidic pH. We also should know, as we will see here, we should end up with a buffer at this point, yes? So again, if you know where you are, you should know what type of problem you're doing. The change here would be our sodium hydroxide, as we have not reached that equivalence point yet. It is still the limiting reagent. Which means at equilibrium, we will end up with 0.0025 minus 0.00215, 0.00035 moles, 0 of that guy, and 0.00215 moles of that guy. We're going to get our total volume here. So we started with 25. We added 21.5 milliliters. That is like 46.5 milliliters, I hope. We're going to divide these guys by that converted to liters, 0.046. I get my hand out of the way, 465 liters. 0.0465 liters there. That is going to get us 0.0465, 0.00753 molar, and we'll go with 0.0462, I believe, molar on that guy. Any questions so far? So let us see if our pre-calculation prediction came true. We are left with sodium acetate and we are left with acetic acid, which is a buffer, which is what we would expect to happen at this point. These guys, again, are related to each other as a buffer. Any questions so far? At this point, we can calculate the pH by using the Henderson-Hasselbalch equation. This is the appropriate place to use that equation. And I'm just going to come back this way and clear this screen, I think. There we go. So we have 0.00753, 0.00753 molar for acetic acid. And we have, what was our number there? 0.0462 looks like. 0.0462 molar sodium acetate. All right, so we were given the Ka value of 1.8 times 10 to the minus 5. So we know we could use our Henderson-Hasselbalch, which is the pKa plus the log of the base over the acid. The pKa value here being minus the log of 1.8 times 10 to the minus 5 should be a 4.74 situation happening, giving us 4.74 plus 4.74 plus the log. The one that's the base is which number? Yeah, the 0.0462, and our acid obviously is our acetic acid here. And here we go, 0.0462 divided by 0.00753. Do a little bit of log of it and add a 4.74. We'll call it a 5.53 pH at this point. Any questions on any of those steps? So by recognizing we were before the equivalence point in this particular type of titration, weak acid, strong base, I knew even before I got there that I should end up with a buffer. And again, these are things you want to really think about when you're doing these problems. It makes you feel a little bit more confident as you go through the calculation part as you end up with these things. Also helps point you hopefully in the right direction. Any questions on that there? And again, we could kind of see how we did on this particular one. That is right in between those numbers, so that's pretty good. All right, any questions on this type of titration curve? We have one more type of titration curve to talk about next time.